Hi, I'm Rachel from My topic today is Embrace High Performance Storage with OpenARM. It's about our practice of SPDK on ARM64. SPDK is the Storage Performance Development Kit. It provides a set of tools and libraries to create high-performance, scalable user mode storage applications. This feature is SPDK's architecture. It mainly includes 4 layers. From the bottom up, it's the driver layer, including NVMe driver and so on. And then the broad device layer. In SPDK, it provides several kinds of broad device, like NVMe broad device, AIO broad device, and many others. And then the broad storage service layer, it provides several services for different purposes, like logical volume, RAID, and so on. And the top layer is a storage protocol layer, including NVMe or fabrics. They host SCSI that are capable of serving disks over the network or to other processes. Besides, it implements BroadFS as a file storage service. We know that traditional kernel out states bring always overhead due to context switch, data copy, interrupt, resource synchronization. SPDK can minimize the impact on CPU and memory bus cycles during I/O processing by many by-3 ways. One is that it uses the user mode for storage applications rather than the kernel mode. The devices that SPDK takes control are unbound from kernel space driver, and instead UIO or VFIO driver is used for SPDK to operate devices directly from user space, which thereby eliminates costly kernel context switch. A second is that SPDK runs in a pod mode instead of interrupt mode. When SPDK initializes on each core runs a thread, which is called a reactor. Users can register different pollers on this reactor. Some of these pollers then poll devices for completions instead of waiting for interrupts. And this reduces the related interrupt handling overhead. And the third one is the shared nothing thread model. Each thread operates on its own resources. For thread communications, SPDK doesn't use traditional lock mechanism, but using event ring. For an NVMe device, a hardware queue is only ever accessed from one thread at a time. So, and SPDK can send requests to the device from multiple threads of execution in parallel without loss. And it's these 3 key techniques that help to bring SPDK's high performance. About SPDK, we have contributed more than 70 pages to enable and optimize SPDK on ARM64. And in the following slides, we will walk through our practice about running SPDK NVMe fabrics on ARM servers. In NVMe fabrics, there are different fabrics like RDMA, TCP, and fiber channel. Here I will mainly show our work on SPDK NVMe over TCP. I will show the I/O performance state and the tuning down on ARM64 and our optimization on SPDK NVMe TCP I/O throughput. NVMe is an interface specification optimized for solid-state storage for both client and enterprise storage systems. utilizing the PCIe interface protocol. One of the main distinctions between NVMe and NVMe over fabrics is that the transport mapping mechanism for sending and receiving commands or responses. And for local access, NVMe maps commands and responses to shared memory in the host over the PCIe interface protocol, while NVMe over fabrics uses a message-based model for communication between a host and the target storage device. Currently, we have NVMe over RDMA over TCP and over fiber channel. The three key elements of NVMe is a submission queue, completion queue, and stop fail register. Submission queue is a circular buffer used to hold NVMe commands, and completion queue is to hold the completion status of each NVMe command. Submission queue and completion queue pair can be set in the host memory or in NVMe, but in most cases we set it in the host memory. Each entry in the submission queue is a 64-byte command, and physical locations in memory to use for data transfers are specified using PRP, physical region page entries, or SGL is the scatter gather list. PRP and SGL are both structures to describe the memory for data. In each subsystem, we have only one admin submission and completion queue pair, and there may be up to 64K minus 1 IO queue pairs. NVMe over TCP makes it possible to use NVMe over fabrics across a standard Ethernet network. There is no need to make configuration changes or implement any special equipment. When using a TCP transport, each NVMe queue pair are mapped to a TCP connection, and then NVMe commands and data are encapsulated as a protocol data unit called PDU and sent over a standard TCP IP sockets. On the one hand, SPDK follows NVMe over TCP's protocol to implement the connection initialization process and rewrite interaction process and so on. On the other hand, SPDK implements the queue pair data handling process according to its own framework feature. I mentioned that each NVMe queue pair is mapped to a TCP connection. In SPDK target side, SPDK will create a new socket for each coming connection. Then each socket is assigned to a socket group created on a CPU core. And for posix sockets, epoll is used to poll the events of each socket in a socket group. And once there is data in a socket, it begins to read the data from socket buffer and handle it according to the PDU type. A PDU NVMe TCP PDU contains the common header, specific header, padding, payload, and digest regions. In the PDU handling state machine, it firstly handles the common head and then the specific header. If there is no payload, then is ready to handle the next PGU. But if there is payload, which may include command or dates, it goes to the next stage to handle the payload. We have said that SPDK is designed to be asynchronous, and its data path is lock-free, and it's a user-space storage protocol. Although in NVMe TCP, the kernel TCP state is not lockless, but SPDK leverages some methods to use TCP state more efficiently. And for single socket optimization, one is that uses non-blocking I/O to avoid the thread to be blocked while doing some operations like reading or writing sockets. But this introduces a partial read and write problem. For example, during a poll period, when the write phase system call returns, just a part of data is written into the TCP buffer. And to solve this, some extra phrases are introduced to mark how much of a request is sent or received. And the second is that it introduces pipe buffer to read as much data as possible into buffer at a time to reduce the sys cost. The third is it uses batch writes to reduce sys cost, which is done by merging multi-write way into one. And besides send messages, the zero copy feature is leveraged to avoid user data is copied from user space to kernel TCP buffer when sending data, which minimizes the cost of memory copy. And for multi-socket optimization, each socket is managed by only one SPDK thread to avoid competition, and uses EPOL to detect the events on a per group of sockets with just one sys core. And in URI-soft implementation, we can submit write operations of a group of sockets at a time, but not call write way for each socket. This is our testing environment. We have 6 P46 00 NVMe SSDs and one 100 gigabit Mellanox NIC. We use 4 kilobyte kernel page size and VFIO PCI driver with I/O MMU pass-through, and make sure that there are enough huge pages on the NUMA node while SPDK target runs. This is the IOPS and IO throughput with 4 kilobytes payload size and 128 QDEPs. SPDK targets runs on only 8 cores. And for render rate, we can achieve about 1.9 million IOPS with 24 initiator cores, and render rates we can achieve 0.9 million IOPS, and for mixed rand rate and write with 70% rand rate, we can achieve 1.4 million IOPS. And on such basis, we did some tuning and optimization to optimize the performance. We tuned the PCIe parameters and NIC interrupt affinity and kernel TCP parameters. For PCIe setting, except for PCIe width and speed, we can change PCIe's max payload size and max read request size. It's up to the manufacturer to set a maximum PCIe packet payload size. supported by the PCIe devices. The max payload size limits the payload size when a PCI device sends a packet, and max read request size limits the maximum bytes that one read request can read. For NIC, we can set NIC's TH and RSQ number and queue depth and interrupt affinity. In general, we set a number of queue equal to the number of CPU cores and start interrupt balance service to make the interrupts are balanced on each CPU. But in our test, setting only 4 RS and TS queues and the interrupts bound to 4 cores can get a better performance than binding interrupts to R8 cores. And interrupt coalescence means we can set how long or after how many frames are received. Then it can generate an hard interrupt. And from our test, we don't use the original adaptive one. We set the number, the time according to our case. And besides, we can leverage the NIC's several offload features like TSO, GSO, and GRO. Then it depends on the NIC to do the TCP packet segmentation work, also merge receive TCP packets into a bigger one. This can reduce some CPU overhead. And for kernel TCP parameters, we can set the TCP buffer size according to our applications. And soft interrupt coalescing is about how many packets or how long the NAPR can pull as high. It's set by the net device budget and net device budget milliseconds and device weight, these 3 parameters. And it's different from the hardware interrupt coalescence. And the queuing discipline parameters set the traffic control algorithm and the related queue size, the net device mass backlog, net device backlog, and TC queue length are the queue size. For example, when we insert a new packet, when inserting a new packet into the backlog queue, if the packets in the backlog queue have already reached the number of net device mass backlog, the new packet should be abandoned. And besides, we tuned related SPDK parameters to achieve a best IOPS. Here I just list 4 of them. Encapsulated size means how many dates can be carried in a command capsule. Without it, host needs to wait for an extra ready to transport command sent from the control side, and then sends the date to the controller. And C2H success controls whether to send a response to host after controller sends all dates to host. And enable receive pipe controls whether to use the pipe buffer to reduce these calls. And enable zero copy send means whether to use the zero copy feature of send message zero call. This call. And in addition to tuning the parameters, we introduced some new features to optimize the performance. This one is using the SO incoming CPU flag of posix sockets. We can get a CPU that is handling the dates of a socket in kernel space, and then assign the following handle of this socket in user space to the expected CPU, which can provide optimal numer behavior and keep the CPU caches hot. And with this feature, we can get about 111 to 17% write performance boost for posix sockets and 8 to 12% for during agile test environment. The detailed implementation is that we use a SOK map to record the CPU ID and destination group pair. When doing the SOK group initialization in each core, the CPU ID and SOK group pair is inserted. And then when a new connection comes, when new when new connection comes, we create a new socket for this connection and then get the SOK incoming CPU ID of this socket. If the SO incoming CPU ID hits, which means it finds an entry in the map, then the socket goes to the corresponding group to handle, or if not hit, it gets a group by default round robin method. You can refer to the page link here for details. And this optimization leverages the smooth weighted round-robin algorithm. The default algorithm in SPDK to assign the sockets to different CPUs is round-robin. It means that each core deals with an average number of connections. But from our test, with 8 cores in total, the performance with NIC interrupts bound to 4 cores is better than interrupts bound to all 8 cores. And this means the 4 cores that deal with interrupts have more CPU overhead than other 4 cores. So we expect the 4 cores with lower interrupt overhead to deal with more connections. So we introduce a weighted round robin. Smooth weighted round robin not only ensure the distribution is in line with the weight, also make sure that the nodes are selected evenly in a period. And this algorithm is not complicated. For each node peer, we have 2 attributes, the current weight, which is initialized to 0, and weight that we set for this node. On each node selection, we increase the current weight of each node by its weight, and then select the node with greatest current weight and reduce its current weight by sum of each node's weight. And with this algorithm, for example, there are 3 nodes ABC with weight 5, 1, 1. A final distribution with smooth weighted round robin is A, B, A, C, A, but the original result is CB, A. And you can refer to this 2 links to learn more about the algorithm and proof. And using this algorithm, we can get about 8 to 14% random rate LPS improvement with a set of proper weights. The column, this is the final performance. The column with solid fading is the original performance, and the columns with oblique line fading is the IOPS with tuning and optimization. With 24 initiated cores, the mixed random rate and read-write performance increases from 1.4 million to 1.7 million IOPS, and read-write IOPS reaches 1 million and read-read reaches 2 million. And the following work, we plan to continue to tuning SPDK NVMe factories on ARM64, and also we'll do some optimization with the SVE. Yeah, that's all about my topic. Thank you.